Okay, well, we'll get started. I'd like to introduce Nathaniel Osgood, who's been doing fantastic work in epidemiology, computational epidemiology and modeling. He's involved in CanMods, Canadian Modeling and Disease Network, a collaborator, and looking forward to this talk on ModelCollab.
Very good. Thanks so much, James. It's a real honor to be with you today, and I'd like to thank the organizers of ACT. I'm really excited to be here for the first time and really energized. But it's a special honor to be with you to present together with my co-presenter Xiaoyan Li here, and on behalf of the lead author on this work, John Baez, on our ModelCollab system, which is a system designed to empower, inform, and help communicate with the diverse stakeholders that compose the interdisciplinary modeling teams that inevitably are behind impactful modeling in health and community safety and well-being. And we're going to be discussing our ModelCollab system, this compositional, categorically based system to enable such stakeholders. Now, this is work that builds on the shoulders of a broad team. Xiaoyan Li lies behind the stock flow.jl that underlies this, but Eric Redenkopp, a master's student in my lab, is responsible for the architecture, the high and low level design, and the implementation, as well as HCI experiments to refine the interface for the system. The theory was put into place by John together with Evan Patterson and Sophie Libkind in work with us, and Alex Allegra and Thomas Purdy are other big contributors from our lab. Those of us from my lab, Xiaoyan, myself, Alex, Thomas, and Eric, draw from the Computational Epidemiology Public Health Informatics Lab at the University of Saskatchewan, where I hold a faculty appointment in computer science and another appointment in community health and epi, and with the biomedical engineering division. The motivation for this work is decades in the making, and it reflects my 20 year to quarter century work with a variety of health system partners, about a dozen now, from local up to federal government level across 3 countries. So in Canada, in the US, and in Australia, in informing decision-making and using computational informatics and mathematical tools to do that. Now, one of the big insights from this work is that really the units of success for modeling projects are not the Uber modeler, but the teams, and particularly interdisciplinary teams that draw on people with diverse lived experience and experience as stakeholders within a system. I know from a certain distance, everything looks like a point source in physics, and from a distance of math, probably everything looks more or less interchangeable about people working in health. But it's a very diverse team that you'll have on a modeling project that is impactful. It consists of generalist physicians, to be sure, but epidemiologists, but also frontline public health officers, medical health officers, as they'd be known in Canada. Also specialist physicians, areas like infectious disease or emergency department or critical care medicine. And then allied health professionals like nurses, simply veterinarians for diseases which cross the human-animal boundaries. And one of the most important needs in these modeling projects is to draw on the expertise of these diverse team members. And traditional modeling projects have got great difficulty with that, you know, where model assumptions are encoded as code or as differential equations that are opaque to the modeling stakeholders. And it's of foremost importance that we draw on the understanding, draw on the background, the expertise of these diverse stakeholders to challenge models, critique them, and thereby evolve a model. It's not It's not a failure of a model if problems are pointed out. It's a success of modeling. And much of what we do is participatory modeling, like many others within the system dynamics tradition, that bring people together with models, represented electronically or in physical form, to use those models as boundary objects, to draw out tacit knowledge, and to communicate around these models, refining them. Now, the system dynamics tradition is one tradition in dynamic modeling that is prominent within the health modeling area, and it makes use of three types of diagrams in a very serious way. I've sometimes heard some of my mentors and teachers in category theory say, category theory is about taking diagrams seriously. This is another field where they take diagrams seriously, not only to capture their assumptions, but to reason about behavior of systems. And there's successive diagram types that refine and sharpen how we describe systems and that help us reason about the behaviors we see with systems. Now, there's a burgeoning field, and there has been since the 80s, of visual software to help support system dynamics modeling and these sorts of models. Tools like VenSim, PowerSim, iThink, Stella, AnyLogic. These are all tools that are designed to try to help modelers deal with visualizing software. But there's a number of fundamental issues with this software. A lack of modularity, lack of any ability to compose model pieces, lack of ability to capture the higher level abstractions that are known in the literature as molecules or archetypes. Believe it or not, these different diagrams are treated as solitudes. Once created, a causal loop diagram lives totally separate from the stock and flow diagrams in the project. Even though there's some structural relationship between the two, never has that been formalized mathematically. Despite the team-based nature of good modeling projects, there's a strange adherence to single user support only in modeling packages. The diverse parties within a modeling project need very different outputs from models to make sense of it. But there's really one size fits all imposed in terms of model outputs. And there's an inability to effectively stratify it's very awkward and rigid, and to combine with computational statistics methods. So today we're going to be exploring this new software that we've been building up, and that's operational. We're starting to explore its use with some of our projects, eating our own dog food, as it were. And the model we're going to be building up has inspired some work that we've done with computational statistics combined with dynamic modeling for all the provinces across Canada individually, and for our province on a particularly intensive basis, and for First Nations reserves, for our Indigenous population across 6 provinces, for the federal governments of Canada advising. For those interested in learning more, you can look at this paper. Those interested in the mathematics of this are referred to an ACT 2022 paper, which provides the basics of it. But really, my goal today is to show this tool. And I'll be relating it a little bit to the underlying category theory. I'm certainly glad, Xiaoyan and I are glad to answer questions about that. But really what I want to do is show a tool that doesn't require knowledge of category theory, doesn't require awareness of category theory. And it's designed to empower people from all walks of life. So we're going to go create at this site here. It's a web-based tool. I'll be describing some of the technology stack later. And we're going to create an SEIRS model. And this is going to be for this conference. I'll provide people access if they're interested in seeing it. And having created that, I'm going to open it, okay? And you'll see a canvas here, and you'll see a palette of items that we'll be using to build up the diagram. And one of the first things you may see is that this is a real-time collaborative system. And Xiaoyan, here in the front row, one of the key people behind this system, is is laying out pieces of the system even as I've been talking, and I'd better get busy to catch up with her here. So we're going to be describing a model where people progress from a susceptible state to a state of latent infection called exposed, or E. And then we're going to then proceed on to elaborate on my part the infection transmission components. So I'm going to add a flow from susceptible to exposed, which represents new infections. And I'll prettify it a bit here by going and dragging the name down here. Now, we're going to use some of these other elements from the palette. And what some of the first are parameters. Encoding parameters as such lets us have different scenarios to make different assumptions about the parameters. And the first I'm going to add is something called total population, which is of significance. And this total population, marked with a P as a parameter, is going to have a value of 1.2 million, which is the approximate population of our province. And we'll further be putting in a parameter that is another important governor of the spread of infection, which is contacts that a susceptible has per day. Now, you'll notice as I articulate these are visual values, and they're designed to communicate to interdisciplinary stakeholders things about what quantities are used in the model, what assumptions we're making about these quantities, and to make scenarios easier to define with alternative assumptions. Now, beyond this, I'm going to need to reason about not just the total number of contacts that a susceptible has per day, but also the number of those contacts they have with infective, something that's known as discordant contacts per day in the language of the health sciences. Now, that you'll notice, for that, I didn't add a parameter. I added what's called a variable, dynamic variable or auxiliary variable. And this is an endogenous quantity. It's something that's computed as the model evolves, but it's designed to communicate domain understanding so that domain stakeholders can reason through some pathways of understanding by which infection is spreading. So we're using terminology that will be familiar to them. Discordant contacts per day depends on the number of contacts per day, but it also depends on something else, which is the prevalence of infectives in the population. So I'm going to add another dynamic variable. And meanwhile, Xiaoyan is going and elaborating the model below. So the prevalence of infectives. That's a bit different than the prevalence of infection. After all, people who are in a latent state of infection are infected, but not infective. But I'm going to distinguish that via the name. And we're taking into account discordant contacts in the sense of contact between a susceptible and an infective. Now, prevalence of infection in turn depends on the total population, but it further depends on the number of infectives here. And each of these dynamic variables is associated with a formula. So the discordant contacts per day is simply contacts per day times prevalence of infectives in a long-standing assumption introduced by Kermick and McKendrick in the 1920s and maintained ever since. Prevalence of infection. Anyone want to say what would be the prevalence of infectives? Anyone want to guess what that is, given that it depends on this and this? A formula for it? Okay, I'll take you out of your suspense. It's I divided by the total population here. And I'm going to quickly fill the rest out so we can get on to more interesting uses of this model. So another factor that's going to govern spread of infection is transmission probability for each of those discordant contacts. And then we're going to put in place a quantity that's widely known across the health sciences, mathematical epidemiology, but also in infectious disease medicine as force of infection. And this is really a temporal probability density, or a hazard rate for those familiar with that term as used in statistics. So it's force of infection. I accidentally, I'm in the wrong mode. This is a modal-based system, kind of modeled after some other system dynamics packages, and I created a few too many variables there. Okay, this one should be called, this one is an extraneous one, and we're gonna have a force of infection. It's going to depend on the discordant contacts per day and the transmission probability, okay? And the force of infection is just gonna be the multiplication of these two. So, whoa, hey, I don't want that. Okay, force of infection is just given by transmission probability. And maybe, Xiaoyan, you could hitch up the force of infection to the infection flow when you get a chance. Okay, and there we go, discordant contacts per day. Okay, and there we go. And Xiaoyan, I see you haven't had a chance to fill that in, so I'm just gonna connect S to this. So we have a force of infection. Each susceptible is subject to some probability per day of getting infected. And we will go and now seek to have that also depend, so the number of new infections will depend on the number of susceptibles, reflecting that. And the formula for that will reflect that dependency. And there we go. Okay, so here we have a, thanks. Awesome. Welcome to the modeling team, James. So I'll clear that off, I think. This is a model which is now parameterized with default values for each of these parameters. It's also got these equations which reveal domain meaningful terms. And Xiaoyan has filled in some formulas for the rest of these that basically reflect assumptions that the residence time in each of these states, EIR, is exponentially distributed in what's called, in system dynamics, a first order delay. Now, this is a model that is encoded notably as data. So behind this model, you might not guess it by the interface, is a whole edifice of category theory. The one I'm going to feature at the moment is the C-sets or atchets, attributed C-sets within ModelCollab and algebraic Julia. So we have a schema category, which has objects like stocks, flows, dynamic variables, parameters, and each of them, it's a Copree sheaf. Each of those maps over to a set, and we have functions between various ones. Some are monomorphisms, for example, from inflows to flows or outflows to flows. All outflows are flows. But as many of you will know, probably almost everyone, this can be encoded or be described, this Copree sheaf, in this sort of the form of a database encoding. We are using attributes to define things, which adds a bit of texture, and that provides a great deal of extra flexibility. Okay, now having done this, having encoded this model as data, something that really is not accessible with existing tools, we can do many things. One of the things is more prosaic. We can look at the code for the model. We'll be coming back to that, but another thing we can do is define scenarios. We can interpret this model in different ways. And in ModelCollab, we expose just a subset of the mechanisms that are available in stock flow.jl. And the main one is right now to interpret this model as an ODE, as an ordinary differential equation. To do that, though, I have to define another construct, which is scenarios. Scenarios are these reusable packages of assumptions that we pair with models, and which allow us to use the same model with alternative assumptions. So there's commonly a baseline assumption, makes default, sort of business as usual assumptions, and then there'll be various alternative assumptions, perhaps associated with, for example, interventions, public health measures of different sorts, or assumptions about the evolution of a virus, et cetera. So I'm going to edit scenarios, and the first thing I have to do here is add a scenario. So I'm going to add the baseline scenario, and then I'm going to go and select it, and I need to set, not just look at the parameter values, I'm going to be using its default values, but for the parameters, but I'm going to set the time horizon so it finishes at 500 days. And so this is going to run from day 0 to day 500. And having done that, I could go select that scenario as my kind of the scenario I want to use for running this model. And we can go then and run the model. While that's running, I want to go open up this code and just give you a sense of what it consists of. So the code that's exported here is stockflow.jl code, using this edifice built up by Xiaoyan. And it uses Julia macros in this @stock and flow to declaratively characterize a model, in this case textually, corresponding to what we see graphically there, which specifies the stocks, the compartments, the parameters, the dynamic variables or auxiliary variables, and the flows, in a manner that's fairly visually transparent. Now, having done that, I see that it finished running, and we can go and examine the output from this model. So this model, together with the scenario, which indicated to make use of the default assumptions about parameters, in this case, being a baseline scenario, provides enough information to interpret this model as ODEs. Now, in stockflow.jl, Xiaoyan structure, there's a number of other sort of semantic domains to which we can map these. We can convert them to causal loop diagrams in a simple form, preventing those from being solitudes as they traditionally are. We can take a model like this and extract other features of it in principle. We haven't implemented too many of these semantic domains yet, but we have the flexibility to do so. Similarly, for causal loop diagrams, we've implemented a couple of semantic domains for them, which we can use to analyze, such as associating polarity with pathways and extracting loops, et cetera. So we get mileage out of encoding these models as data. And it's going to afford us a platform for building on additional semantic domains to allow us to do things like loop gain analysis, eigenvalue elasticity analysis. But there's something very important that additionally comes with this encoding of a model as data, and that's the ability to compose a model, stratify a model, et cetera. These are traditionally either not available or very painful techniques. So I've just gone and I've imported a model previously published by us. You could imagine what we're shooting for is to have an ecosystem of these models, some of which are published in the literature that we can draw on. They're tested, they're documented, they're evidence-based, and we want to be able to reuse those components. We might want to swap components for certain assumptions and examine the impacts on model results instead of building a model out of whole cloth, in a monolithic way. So I've just imported this model, and right now they're just the co-product of them that are sitting next to each other. But of course, what we want to do here is compose them, glue them together using structured co-spans as supported in ModelCollab and in the algebraic stockflow ecosystem. So what I'm going to do here is I'm going to identify this stock S in the imported model with this stock S here. And I have to say, we fall grievously short in terms of the visual appearance here, and we're working on it, but we didn't want to destabilize the code base for today. We're going to identify this parameter, total population, with this parameter here, and we could futz around and probably prettify it in some way, but I think in the interest of time, I'll show you something more interesting. So here we have taken our model and we've composed it with a model that involves vaccination. So we had that original model, we layer in this model with vaccination, we take their push out in the context of structured co-spans, and we can look at how they interface. If you were to go look at the code here, what you could see is that we actually are using we're encoding two models, and then we're using a domain-specific language for composition and specifying the feet of the structured co-spans by which these open stock flow models interface together. Beyond this, though, we could go and import another model, which is going to make assumptions about asymptomatic infectives and posit a different pathway for asymptomatic infection. And I hope you'll forgive me our aesthetic sins here, but we will go unify this E stock here, excuse me, I should have done it the other way. So I'm going to unify this E stock with this E stock, and this R stock here, okay, with this R stock. So we've once again glued these together using the remarkable richness of structured co-span composition. And we have, in addition to the traditional pathway of natural history of infection by which one becomes fully infective, you now have an asymptomatic infectant. And if we were to look at the code for this, what you would see is not just two, but three models, and them composed together out of certain components. Now, having done that, we can go back to our scenarios, and we can see that the scenarios now include assumptions about these parameters in these different pieces. Oh, did someone displace that a bit? It suddenly traveled down my screen. I have a feeling I'm not alone on here. Okay, I'm going to select this scenario. Pretty please don't like mess it up too much, right? Yeah, right. So here we have three models encoded. We're specifying the feet of the structured co-spans in a way that combines them, and then we're going to be running them. Now, this is going to take a bit of time to run, and I hope no one else is trying to run the same model at the same time. But what we're seeing here is the ability to take models, package them up as components, and compose them. By a similar logic, we can stratify a model in a fairly modular way. Traditionally, stratification is rigid, it's awkward, it's painful, it obscures the logic of the underlying flow of the model, and it gets in the way often of communication. And with our stratification mechanisms in stock flow, we have a much, mumble. Okay, well, we may have to run it one more time for good measure. But we have a way of stratifying that avoids a lot of the cursive dimensionality we see with traditional stratification mechanisms. So maybe while this is running, I'll just make a few remarks. We're running out of time. What is this about? It's about empowering team-based modeling, because that's impactful modeling that draws on the understanding, the expertise, the lived experience of diverse parties. And we work to empower that with diagram-centric modeling that communicates to all members of our team, encoding those diagrams as data so that we can compose them, so we can stratify them, so we can share and reuse them. We're also having a separation of concerns, so different parties can work on different components of a model, and a separation of syntax and semantics, which lets us analyze the same model with multiple different semantic domains. And finally, we've layered on this real-time collaborative interface, which, okay, third time's the charm. This real-time collaborative interface, which I'm getting a network error if no one noticed, real-time collaborative interface, which allows us to leverage the interactions of multiple parties across a team.
Thanks, Nate. I'm sorry to the next speaker. I was so engrossed in Nate's talk, I fell down on the document. One sec, Nate.